matter holds, right? Andersonbound.com, that website I have shared. For a transaction to be added, does it need to be validated? And does those validated transactions only are added? All transactions, they come to mempool. I talked about two databases which are maintained. One is called mempool, and the other is called UTXOset, right? So these two databases are maintained. So all the transactions come to mempool, and the miners pick up a set of transactions and add it to their block, and then create a Merkle root and do that process, right? So that is what happens when validated transactions are of 2 MB. They are ready to be blocked. Yeah, 2 MB, 3 depends on the size. A set of blocks, set of transactions are picked up. Now, what is presently happening is people are picking up those transactions which are going to give more transaction fee. So, like that, there is a slight variation which is happening. Nonce I have explained. This thing is explained. Selfish mining I have explained. DDoS attack I have explained. Network privacy as compared to other privacy preservation models, yes, definitely, because a lot of anonymity is there, but definitely not as much as Tor provides. So people are trying to combine Tor and blockchain. It's going to be a deadly combination. So you can examine that when you want to go for privacy preservation, anonymity, you can look at Tor and of course blockchain as well. How smart contracts deduplication is handled. Yeah, obviously, the attacks on smart contracts, shortly I will explain. But then deduplication, how they can be handled, there are a variety of attacks. So we need to try to look at how best we can try to understand the language and understand the functionality behind that, and of course now I am going to talk about scripts also a little later, and atomic swap, which is an important concept which we want to look at. So that is if we want to decrypt some file, can I submit this as a problem to blockchain? No. So you can do a lot of things using blockchain, but everything that you do in blockchain comes with a cost. So you have to pay a transaction fee, otherwise nobody is going to touch your problem, right? So that is something that you need to understand. Yesterday, Dr. Sushmita was talking about overhead, right? So any research problem that you want to address using blockchain, you need to also look at the transaction fee that different ethers or Monero or any of these blockchains will address. Or you set up a private blockchain and then you can do it. Of course, that also comes with a cost, right? What is hash? Please refer to any cryptography initial textbook, because I think that will be beyond the scope of this lecture. If we make use of blockchain to store data related to insurance company, is it necessary to mine? No, you don't need to mine, but you'd have to pay transaction fee. Whenever you want to store a record and retrieve a record, you will have to pay a transaction fee. Otherwise, there is no problem. Mostly to retrieve it is free because it is lying in the ledger. But then you have to ensure that people don't understand it, because the insurance details should not be public. So you must ensure it in hiding. But as a data component, you can store them. If anyone can transfer 1 Bitcoin to a friend, so how many Bitcoins get reward miner? No. Whenever you make transactions, only transaction fee is going to the miner. A miner, when he adds the block, that is because he's solving the encryption puzzle, he's getting a reward of 0.25 as in Bitcoin blockchain, right? Eclipse attack, you can read. I will share with one paper with you, which talks about a lot of attack surfaces on blockchain. So please go through that, and then you can try to build an Eclipse attack and see how it goes, right? Why Ethereum is based on proof of stake? Proof of work algorithm needs a lot of power, and there may be malicious users. Proof of stake will have more honest miners, because if I have more stake, I want the blockchain to survive for long. So I will be honest. So I will not do any dishonest practice, and hence the proof of stake algorithm. It is one mechanism. That's your choice. If you want, you can use it. If you don't want, you don't have to use it, right? So every block has a Merkle root. All the transactions will result in the Merkle root value, right? You can read more about that. As I share the slides, you can look into that, right? So, or no, one root for entire blockchain? No, every block will have Merkle root calculated of all the transactions. So if you want to make one transaction change, the Merkle root will change. Because the Merkle root will change, so that's what I talked about, the avalanche effect, right? By whom transaction is verified, other miners will verify the transaction, right? Smart contracts, how recognize it is fake or true, you have to depend and trust the smart contracts, because you are writing those smart contracts as an agreement between you. So anybody who's providing a service, let us say government of India is wanting to make all the registration records on Ethereum available through a smart contract. So you will have to trust that smart contract, that whatever data it is providing and whatever data you are storing there is going to be safe. So obviously the trust is one aspect, because whatever is stored cannot be changed. So that is the strong trust that is generated, and hence you can build on that. But obviously the smart contracts are themselves not implemented correctly, and there may be vulnerabilities. So that is something that you need to test, and that is a problem with any software or any hardware that is there. So I have answered all the questions. Aparajita ma'am, any questions that are there on your side, or shall I continue?
By whom I think you can continue, but I have been telling these people that they should write to you so that they can get. Anyway, there is one question by somebody, name is not clear, by whom transaction is verified. I think you have already.
I have answered. Miners do the verification of transactions.
If it's smart contracts, then how contracts recognize it is whether fake or. So he has already answered this question.
Yes.
Yeah, and no more questions. Yeah, no more questions. Thank you. You please continue.
Sure. Yeah, so you can get, as I mentioned, the transactions details you can get. Blockchain is replicated at each node. Observer can use the transaction history in the blockchain to find the topology of the network. So based on that, somebody has done a geographical location mapping. They could not get the exact who is the person who is operating the network and all, but they got the location, geographical location. Like that, they have found out how many nodes are existing at a certain point of time. This must be like September 14, 2019. They found that most of the Bitcoin nodes are available here. These are the things, and by country, these are the countries which are actually operating, and about 9,054 nodes were active at that point of time, switched on, turned on, right? So like that, this kind of a network can be created. So it's a privacy issue. Actually, we are able to identify which geographical location people are mining and people are doing. So this is a kind of data, and if you can drill down now, once you go to United States, you may get different locations and all that. So though we don't know who the individual is, we know from where he is getting. There are some other privacy attacks where you can look at transaction network can be developed to study the flow of bitcoins in the network, right? So user network can be developed to study the ownership and spending patterns of the users, because as you see here, this is the origin. It is going to this and this, and different addresses are coming. So most of the time, when one coin goes somewhere else, the balance is transferred back to them. So usually the addresses are same. So using transaction patterns and information gathered off the network, an adversary can attempt to de-anonymize the user. So that's the possibility that is there. You can map your Bitcoin addresses with the real world entities, making it pseudo-anonymous. So somewhere there can be a kind of a linkage between the physical network address and their public address that is there. You can try to create a link. So slowly you can't make it fully anonymous, but you can actually get it pseudo anonymous. You may be able to guess who the individual is, right? And by and large, vendor addresses which are scrapped on the internet. So this may be a vendor address. So most of the addresses are coming to this address. So you know who is buying from these products who are buying. So that kind of mechanism is there. All input addresses belong to the same user as transactions are generated from one source. As you look at it, 5 addresses and they are giving to one address and some bits are given. So why do these 5 things are coming together in a single transaction and sending one address? So by and large, these 5 addresses may belong to the same one single gentleman. So this is a kind of network analysis which can be possible. And similarly, you can have these 4. There is an original address, and you are sending to some recipient and sending it to remaining. The remaining one is going, so he is coming here, but it is a different address. So you can guess that this individual and this individual are same. Similarly, here another address change, another recipient. You have sent friend 1, you have sent friend 2, but the remaining you have sent yourself, and you have sent yourself. But each time you are giving a different address. So I can guess that 3 addresses belong to the same individual. This is a kind of transaction analysis you can do. All the transactions are available to you, and then machine learning algorithms or these series algorithms, time series algorithms, or some of these things are very much available, and you can try to build the chains of things, right? He has made transactions to so many people, they have made transactions, so you can build a big topology network, right? A lot of illegal activities can be done using cryptocurrencies. I have discussed this. Maybe like you can do a lot of scams and all those things. So it's very difficult, and there is no central agency to go back to and do that. Now, wallet is another issue that we use. Wallet is a file that contains credentials. You can have both kinds of wallets, software wallets like your Paytm or Google Pay. You can have hardware wallets, which are like your pen drives, right? So basically, these wallets store your private and public keys for a blockchain. And in some blockchains like Bitcoin, the wallet file is stored unencrypted by default. So this is another big issue. So sometimes when you are using your wallets on a system, somebody can attack your system and get into your network and then access the what do you say, wallet, and steal your private keys. Once they steal your private keys, they become you. Right? It's like your identity. The only thing about a personal identity in blockchain is the private key. Public key is anyway announced. So once people are able to guess your private key, they can take care of the entire transactions on your behalf and steal the money. If an adversary steals the file, they can sign the transactions and they can spend that balance. It is like your internet banking password and transaction password. Once they are stolen, then anybody can make a transaction on your behalf, or anybody can guess those transaction passwords also and do it. Sometimes we usually use family members' names and specific symbol notations and all. So it's easy. Of course, I will skip this part because DApps and all those things were covered, right? What I am trying to introduce in smart contract is that smart contract we use Solidity, and I think Mr. Samir Jain has taught you well on that, and a variety of codes you have already run, and you would have seen it, Remix and other editors, right? So Solidity and Viper, right? So and then you could have read these. These are some what do you say, the documentation you can read here, and you can study and run those codes and some sample codes. This is one sample code I have mentioned here. So smart contracts are can also be attacked, and there are some vulnerabilities in the Solidity programming environment, and also so one specific thing is not secure. It can lead to some attacks, right? The Solidity code can be attacked. They are called re-entrancy attacks. So there are some functions called call.value, and you can make some recursive calls to that, and they had what is called a decentralized autonomous organization attack, DAO attack, on the Ethereum, which happened, and it was very popular, and it happened in 2016. So it was like very difficult. So in less than 3 months, the decentralized autonomous organization was hacked, and $60 million of Ether was stolen, right? So this is the kind of code. Maybe you would have written some codes. Maybe when I share the slides, you can try these codes and check it out of how these DAO vulnerability was exploited and how the withdraw balance, it calls back again and again, and what happens, the money is debited. It's like going to a ATM and then you place your ATM card and withdraw money. After some time, again some more money is coming out. After some time, some more money is coming out. So these kind of vulnerabilities do exist, and you have to be very careful when you try to do that, right? So that's what is the question. There can be attacks on overflow attack. So Ethereum smart contracts don't support values greater than 2.256. So buffer overflow attacks can be created by having a really large value, a big integer and huge integer, and those kind of things you can create. After it crosses 2.256, that kind of a value, then obviously it fails. Ethereum cannot handle it, right? Forcible balance transfer, the contract is vulnerable. Forcible balance transfer can be done, and limits can be exceeded, as I mentioned in the previous case, like some of those attacks. Those attacks can be there. Smart contract can be written with malicious intent, causing denial of service attack. So the smart contract itself will cause the system unusable. So that's something that you can look at. So let me introduce you one important concept before we go to atomic swaps. This is Monero. Monero is a privacy preserving blockchain because there is some privacy attacks which can happen. And then there is a pseudo anonymity which is there. So Monero tries to create and enhances privacy using what are called stealth addresses or single use addresses. You can also have ring signatures and confidential transactions. Yesterday, Dr. Sushmita had discussed something on confidential transactions. Slightly difficult for you to understand, but the first two are very easy. Let me take you through them, and then I will leave confidential transactions for those to read. I will share some some papers. You can read through them, or of course you can search on these interactive, non-zero interactive proofs. But what are these Monero stealth addresses, right? So what is happening is, here we try to see that there is a link which is coming in. Alice and Bob are making transactions to Charlie. There is one address, transaction 1 and transaction 2. So the whole world know that transaction 1 and transaction 2 are going to the same address. So this is what is called linkability. The ability to link all addresses held by a single person by analyzing the transaction. So we know that if transactions are going to the same person, so it appears that these two people are linked to Charlie. So that kind of these addresses are linked with these addresses, that kind of a thing you can try to create. But in Monero, it comes up with an option that they are unlinkable by the network. So you get two different addresses here. So Charlie has one address here and Charlie has one address here. So when you look at two transactions, it goes to two different addresses. They appear to go to two different addresses. It may be going to Charlie's address only, but it's appearing to go to two different addresses. So when the world looks at it, it's no idea where the transactions are going. Alice is sending to somebody, Bob is sending to somebody, we don't know who they are. So there is no linkability which is created. This may not be on the same transaction, this may be on different transactions also. But if you study Charlie's transaction, who is sending money to transactions to Charlie, they can understand that Alice, Bob and Charlie are linked. But if Charlie has different addresses for different people, Alice is sending to somebody, Bob is sending to somebody, but we don't know that it is the same Charlie. So this is one process, that is using stealth addresses, you can provide unlinkability. A different destination address for each output is derived from one Monero address of the user. Only the owner of that Monero address knows the output is for him, because he has the view keys, the private key he knows. So nobody can tell these outputs are going to the same person. So you are trying to build privacy into already a very anonymous blockchain. So that's something which is advantage of Monero. The second thing is untraceability. Untraceability is, there are some transactions, ABC transactions, they are coming to Charlie's address using a single transaction. So they are ABC are some addresses, they are coming. So traceability is ability to trace funds held by some person by analyzing the transaction data. So Charlie is getting some funds, he is getting some funds from ABC, right? So now they are with, so transaction 1 is spending funds received in transactions A, B and C. So A, B and C are sending some this thing, and it is coming from that sources. Those addresses are becoming one source here, transaction 1, and transaction 1 is going to Charlie. So Charlie is receiving money from transaction A, B and C. But what actually happens is all these transactions A, B and C will be multiple addresses, and then it will go to multiple addresses, and then they will go to Charlie's address. So if multiple addresses are going to multiple addresses, finally combining into transaction 1, we don't know where those transactions are coming from, so there is no traceability that can be used. So this is the second principle that it is called use what is called ring signatures, right? We will look at what is ring signatures. So at least one real participant and others are called mix-ins. Mix-ins are outputs from some previous transactions that already been used. So they are null and void, so they are not considered. So even if people search, then they will see some addresses and they are getting confused because they are already coming somewhere else also. They are coming somewhere else also. Only one real participant, others are mixed. So ring signature is used to create the transaction. So there are multiple addresses coming in. They are going to multiple places, and different people will verify their address. So Alice, Babbitt, Carol, they are signing, and for a verifier, no way to tell who the real participant is. 3 people are locking, 3 people are unlocking, but only one person is actually here and one person is actually here, and they will take the actual value. So what you need to do is find some outputs in the blockchain with the same amount X as the output A you want to spend. So there are some already spent transactions. So you know that you want amount X. So whatever amount X transactions are there, you take them together. These other outputs are called mix-ins. You have your transaction, which is the valid transaction. All similar, maybe you want to transfer, let us say, 2 bitcoins. All transactions which have 2 bitcoins, you copy from somewhere else, previous transactions, and copy them together, right? All mix-ins have the same value. So you can add up to 4 to 25 mix-ins. So 4 to 25 mix-ins are coming, and then you sign it using a ring signature. What is a ring signature? Signature is something like that. It is easy to verify that at least one user from the inputs have signed this ring transaction. Not easy to find which one has signed. That is a problem. 4 people are going in, 4 people are reading it. Only one person is the valid one person is reading. But who is that one person? We don't know. That is what is the advantage of a ring signature. This is the example here. Now output A, output B, output C, they are all same. So all inputs mix in, and real input are of the same value. The real input is actually output 0, and output 0, output A, output B, output C. Everything is same value. A, B, C, and O are same. So they are going from sum to sum, sum to sum, sum to sum. So you are actually transmitting, A, O, B, C are addresses, and the Bitcoin transactions are X. X is being transmitted. So mix in 1, mix in 2, mix in 3, they are mix in values. But for the outside world, they look at 4 people are making a transaction of X value. And finally, when you look at the final transaction, they are all clubbed, and then an X transaction is coming out. And finally, that X transaction is going to Bob. But within these 4, who has spent, who has sent, we don't know. So that is what is called a ring signature. There are 4 transactions here. So a reference of output A or O or B or C. But we know, or we are able to see this diagram and know that it is output O. A, B, C are not there. A, B, C are some unused, already used transactions. They are not valid. So X goes, X bitcoins go here. All X's are going. Actually, 4X must come out, but only 1X is coming out. So anybody who looks at the transactions also realizes 3 bogus are there. But which are the 3 bogus? We don't know. 3X should come. 3X has not come. 4 mix-ins, sorry, 4 addresses. So give a 4X X bitcoins are transmitted. So 4X bitcoins must reach, but only 1X bitcoin is going out. So 3 of them have played havoc. So, but then which of them is not known. So that is what is the strength of ring signature. And lastly, we want to keep the transactions confidential. We want to hide the amount also, right? So I don't want to know that I have made a transaction of 2 bitcoins. I have maybe publicly I hide, but I want to hide this transaction. So what can we do is, Monero uses what is called bullet proofs, right? Non-interactive, zero knowledge proofs, right? We don't want to mention 2 bitcoins, but we want to ensure that 2 bitcoins are transferred. So that is what is, there are alternate ways of finding out. So that's what I looked at. Non-interactive, zero knowledge proofs. So they are used to create confidential transactions, encrypted input and output for a transactions are given in a range, and without revealing any information about the numbers, you try to do it. And it uses what is called a Pedersen commitment. So the actual values are not mentioned here, right? So there is a kind of what is called a present commitment. Transaction amounts are hidden, transaction graph is public, but public verifiability of transaction validity by other users and miners is also possible, but the actual transaction amount is not revealed. That's the basic idea. So this is something where you try transaction validity conditions, outputs are positive, sum of inputs is greater than or equal to sum of outputs, some kind of condition is mentioned. So the actual amount is not known, but the confirmations can be done. I think we will not go into this. Let us leave it. You can read about the present commitment and go through this thing. Basically, they are homomorphic, as you would have studied. So let me go to the next part. So this is a kind of algorithm yesterday that Dr. Sushmit also discussed. So you can take it down there. So let me go to the next aspect that is on atomic swaps. Is another interesting aspect as we look at. Yeah. So what is this aspect here on blockchains is there are a lot of scripts, right? And we will try to understand some of these scripts. We have understood Ethereum, you would have come across smart contracts, but there are other scripts like HDLC and script. Script is a programming language for blockchains. For Ethereum, you have Solidity, like that. You have this thing. So let me take you through this thing. So Bitcoin transaction script language is called script, right? So it's a stack-based execution language. We will show you. Of course, stack is inherently used, but it's a stack-based execution language. It's a simple language with limited operations, designed to be limited in scope and executable on a range of hardware, maybe like an embedded device and all. It's possible. Requires minimal processing, limited in operations as compared to modern programming languages. So that's it's not like Python or Solidity. Also, script is very simple as you look at it. So here is an example of a transaction. Somebody was asking me a transaction, right? This is how a transaction looks like. This is one address which has these many bitcoins. It's sending to these two addresses, and this is how the bitcoins are divided. If you add both of these, this amount will come. Right? So you have this transaction, so it is going back to the same address, right? So this is what I told you, right? Somebody is sending to a friend and himself. He is sending a friend so much, and the balance is sending to himself. So this is an example of transaction, and this is how a transaction can be locked, right? So we can see how the transaction locking can be done. Now we will try to understand that. So remember these three addresses, 1, 2, and these three are addresses. These three are the amount, right? Now, there is a locking script. Locking script is, it can be directly run on the blockchain as a transaction, right? So what happens, it is a spending condition which is placed on the Bitcoin transaction output. On a condition, only this transaction must be done. This transaction must not be done for all cases. Like usually whenever a transaction like this, the transaction is successful. Whatever it is, they are taking. But along with that, you can put locking script. The locking script will look at some conditions to be fulfilled. If the conditions are fulfilled, the script will be executed. Otherwise, the script will not be executed. That means the transaction will not happen. Let us say this is a locking script. It specifies the conditions that must be met to spend output in the future. Now, I have made two transactions. These two transactions I am spending, but along with these two, I am locking scripts. Locking script for this, I put one. For this, I put 1418, 1BC4, right? 1418, 1BC4. For each of them, I put a condition. What is that condition? So there is some condition, duplication and hash 150, some value. So this value should become, and then you should verify whether it is equal, and then you should check it. And if they're all satisfied, then this transaction can be taken up, right? Similarly, for this transaction also, there are these values. So these values are different here. Different hashes are included. So you have to check whether these two are there. So this is what is given in what is called, it's also called a script of key, as it usually contains the public key or Bitcoin address. It contains the public key or Bitcoin address, and hence it specifies that, right? So specifies the conditions that must be met to spend the output in the future. Now, how do we do that? So now, when we want this thing to happen, there is an unlocking script, right? The unlocking script, it satisfies the conditions based on an output by a locking script. Locking script is the certain hash has to be generated, and you have to check whether it is equal to that hash. If it is equal to the hash, then the script is the unlocking script, and the locking script checks. So that is what happens. So allows the output to be spent. Part of every transaction input mostly contains a digital signature produced by the user's wallet using its private key. It's also a script signature because it contains the digital signature. So this is what actually happens. So let us see how it proceeds, right? So this is the address, and this is the value, and this is the what locking script. Now this locking script is put here, right? The locking script on the input applied on previous transaction when input UTXO, the unexpected transaction output, was created. So first time when the transaction is created, so this locking script is placed. The unlocking script on the input applied in this transaction to spend on it. So you have to run this unlocking script. You have to supply some values, and if you are able to give the values correctly, then you will be able to unlock that transaction. The transaction will take off. So as you understand, this is an unlocking script, right? So you look at the locking script. This is the locking script, and similarly you will have this is the locking script. Okay, 74525, right? 74525, right? So this is locking script, and this is the unlocking script, right? So this is what happens, right? So when you look at it now, how do you understand the script? Script consists of two components, right? One is data, that is public keys and signatures, and then some opcodes, which are some simple functions that operate on the data. So you have a stock kind of a mechanism. There is an unlocking script and there is a locking script. So you can try to understand the difference, right? So let us see an example. Data is pushed onto the stack. Okay. Data is always pushed onto the stack. So this is the data part, right? And the opcodes can pop the elements of the stack. So that is what, as I told you, the scripting is a stack-based language. So what happens? The opcodes can pop the elements. So related to this, so you can pop the elements, and you can optionally push new elements onto the stack as well, right? So that is what happens. So a script is valid if the top and only element left on the stack is a 1 or greater. So finally what happens? You get 1 or some greater value is there and the stack is empty. So you just understand what is happening. Please observe it again. This is starting. So when there are opcodes, pop happens. When there are this thing, again input happens. Equal verifies an opcode, so it verifies top 2 and checks whether they are equal, checks the signature, then results with a 1. If it is 1, then the transaction is valid. If it is any other value, then the transaction is not valid, right? So hopefully you have understood how the script is working. So the script is invalid. That means the transaction will not happen if the final stack is empty and the top element on the stack is 0. And there is no element more. There is more than one element left on the stack at the end of the execution. It is not 1, but there is some element, right? Some other element is there, or the script executes prematurely. There is the stack failure somewhere, and then the script executes prematurely. Top element is not 1 but 0, then also it fails. The final stack is empty, no value is there, then also it fails. So that is how it is. Maybe you look at it once again. Yeah. So the whole code is, then you are checking whether the duplication, then you are checking the hash value, then you are storing it, then you are getting two values, you are checking whether the values are equal. If they are equal, then you are checking the signature. If the signature is equal, you are pushing 1. And if 1 is there, then the transaction is completed successfully, right? So there are different scripts. Again, there are P2 PK scripts, pay to public key. There are pay to public key hash scripts. So you can directly address a public key, and if the public key is verified, you can pay. If the public key hash is there, if public key hash is verified, or you can pay to script hash, or you can also have P2 WSH scripts. Right? There are another type of scripts which are there. So this thing. So PK script, pay to public key script is a script pattern that logs an output to a public key. Right? So you have a public key, and if you check two signatures match, the script pub key and the script signature, so both are matching. It is a simpler version of the PHK locking script. So it's a P2 PK script. So working is something like this. So you have a signature is pushed, then there is a pop. When both of them are verified, you push a 1 onto the stack. So that is how you have. That's what is called P2 PK script. Both are verified, then you push 1. P2 KH script. Okay, that is pay to public key hash script. So pay to public key hash script used by wallets by default when you want to send someone bitcoins. Most common scripts used in this transaction. So you take a hash of the value, then you verify it, and then you sign it. So the script looks something like this. So first the signature goes, then the key goes, then you duplicate it, and then you check it, then you get the hash value, then you this is also pushed. Both of them are verified, both of them are equal. Then the signature is checked, they are also verified. Then you push 1. Right? To solve the owner, to solve the script, the owner of the hashed public key needs to provide the original public key along with a valid signature. So that is what is to be done. So P2 PKH script pattern contains a hashed public key surrounded by following out, of course, like check sig, and you have different values. So like equal verify, hash 160 and all. So that is what happens. Then you can have a multi-signature script, which is so it sets a conditions where n public keys are recorded on the script, and at least m of those must provide signatures to unlock the funds. Also known as an M of n scheme, where n is the total number of keys and m is the threshold of signatures required for validation. So you can go with a multi-signature script. Right? A general form of locking script, setting of an M of n multi-signature, where you have m public key 1, public key 2, and so on, and then you have public key n. It goes up till n public keys. Then you have you can check the multi-sig. Right? So that is locking scripts also, where you can go on like this. So these are 2, and then it goes on with Mohammad's public key, and then partner 1 public key, and like that, and it goes on. And then you have a multi-check, multi-sig. So multiple signatures you can check. Then you come to P2SH scripts. It solves the issues of a multi-signature script. So in P2SH payments, the complex locking script is replaced with a digital fingerprint, which is a cryptographic hash. So pay to a script hash, right? So when a transaction attempting to spend the UTXO is presented later, it must contain the script that matches the hash in addition to the unlocking script. Unlocking script usually used to verify the addresses, but now you have to match the hash, right? The script should have something which matches the hash. So P2SH means pay to a script matching this hash, a script that will be present later when this output is spent, right? So locking script that is replaced by a hash is referred to as the redeem script because it is presented to the system at the redeem time rather than as a locking script. So it is taken up only when it is being redeemed. Again, you have a script there running. So how does it run? So this is how it is there. So there is 1 minute. You can look at that again. Yeah. Sorry, it won't stop actually. The animation won't stop. You can see the animation again and again. So then you can understand. So another copy is maintained. And then you check whether they are equal. Then you put 1 on top. Right. So once the 1 is there on top, then you can get it. Right. Similarly, you can check the multiple signatures, and then you can check what are the values, and then you can push the 1. So maybe we repeat it once again. We maintain a copy of that. About check whether push it, check both of them are equal, then you top it with 1. So that is done. So the copy, then you again take it out, you load this thing, and then you check the multi-signature values. Once that is all done, then it pushes 1, and once you find 1, you can consider. So this is a P2SS script, and there is a P2WSS script also. I leave it for you to read it, but then these are scripts which can be written easily. Based on that, we build a concept called atomic swap. I will come to that. So complex scripts are replaced by shorter fingerprints in the transaction output, making the transaction smaller. P2SH shifts the burden of constructing the script to the recipient, not the sender. And P2SH shifts the burden in data storage for the long script from the output, which is in the UTXO set, the previous transaction, to the input stored in the blockchain. P2SH shifts the burden in data storage for the long script from the present time to a future time. You don't lock it when you are making the transaction, but when it is redeemed, you do it at the later time, in a future time. It shifts the transaction fee cost of the long script from the sender to the recipient, which has to include the long redeem script to spend it. So finally, the redeemer will pay money and redeem it. So that's how P2SH scripts are there. The equivalent is the smart contract. You can look at that. It's a smart contract is a code that facilitates. I have not given much details here because you have dealt with Ethereum and Solidity and smart contracts. So stored on the blockchain, run by every node running the blockchain. Code cannot be changed once written. So guaranteeing immutability. Saved as smart contract accounts on blockchain. So they also contain functions and data that can be executed from user or other accounts, right? So HTLC is another important thing. It's called hash time locked contracts, HTLC, used to enforce time-bound conditional payments, right? So do not require trusted third parties. Used to create programmable escrows. Escrow is a kind of a third party that is mentioned, I think. Okay. Sorry. So the hash time lock contracts, HTLCs, similar to smart contracts, they are used in Bitcoin blockchains. So used to enforce time-bound conditional payments. So you can actually do an atomic swap. I will come to that. Very interesting concept. Do not require trusted third parties. You can very easily do it using a trusted third party. Trusted third party is like a wallet, right? So you store the money in a wallet, and then from the wallet you can do all these transactions. But the actual the problem with these wallets are that the public key is anyway known to everybody. The private key is not known to you also. It is maintained by the